Hi everybody, I'm Ryan McNeil, and today I'm going to go over my Lab 1 on constant velocity. To introduce this lab, let's talk about the purpose. The purpose of this first lab is to apply Newton's laws of motion, first and second, to real-world examples. In our case, this will be done by rolling a ball across a table. We're going to try to verify this with the tracker program and a computational model coded in Python. Now, when the F net is equal to 0, or that all the net forces are equal to 0, this will result in a constant velocity and a change in momentum equal to 0. Below are the derived velocity update and position update formulas that explain Newton's second law in this regard, which is how forces that act on a system from its surroundings can cause changes in the momentum of that system. Now, here's our original tracker video. We have an orange ball rolled across a table from left to right. Now this has a constant velocity across the x-axis because there's no forces being applied. This is because of Newton's first law. To show one more time. Now here's our GlowScript code for our computational model. The code is written using GlowScript, and you can find it by clicking this link. So to start, first, the mass is not going to change the velocity, since that's canceled out by F net equals 0, but I did my best to approximate the mass of the ball. Additionally, the initial conditions, the ball position and the ball vector, were provided from tracker points and calculated by tracker points. So the initial position was 0 and the initial velocity was 0.5. Additionally, down here, the delta t was equal to 0.03, which is because my video was recorded in 30 frames per second. The code on the right is used to show the position and update velocity formulas down here towards the bottom. So we're going to iterate down here, if you look first here, by a delta of 0.03 all the way up to 1.23, so this is a long while loop. And again, we're going to have the net force set to 0. And what we're going to do is we're going to apply the momentum principles, Newton's second law, to update the velocity and the position using these formulas that are here and that we showed previously on the screen. So here are our results. The experimental versus computational graph comparison results. It seems to be a good estimate initially, as it shows the ball moving at a constant velocity until the end. There's a slight deviation due to some friction on the table as we reach the latter portion of the graph, which is going to affect our velocity. Additionally, the experimental seems to be a little bit less consistent, but these graphs are very close correlation-wise. The only difference, as stated, is towards the end of the graph, there's another force acting upon it, friction, which is going to give us different results in terms of the position and the speed. So here are some follow-up questions. So one of them is, one of the questions that is asked is, what happens if you flip the axes? Well, looking back, if you were to flip this axis, all that would change is that the graph would switch slopes. So the data would be reflected across the x-axis and have a negative slope instead of a positive slope. This would result in the same magnitude and other features, but you would just have a different slope. You would still be able to come to the same conclusion as well about there being effects with friction. As for the second question on how many pushes and pulls are added together to get a zero net force, we know that the friction that acts on the ball, we know that there is friction acting on the ball, so the net force is not necessarily 0. But we're not sure what other forces may be responsible for the constant velocity to counter that friction in the first place, since we know that there are other unbalanced forces acting on the system. For example, one of these could be air resistance. So as a result, we cannot say the total number for sure, but we do know that there's friction acting on the ball, so there are at least some additional outside unbalanced forces that are acting on the system. Thank you for reviewing my lab.